All right, everybody had a good 15-second break. Nice. So, I hope you've all been enjoying the presentations thus far. Now it's our turn. So, our presentation was on creating hydrophobic coatings with eco-friendly materials. My name is Akash.
My name's Darren.
I'm Raphael.
I'm Grace.
I'm Emily.
So, to start off, we first need to understand what hydrophobicity is. Now, the other group that did hydrophobicity and hydrophilicity covered a little bit of this. This is just like a little bit more detailed diagram explaining this concept. Sorry. For right now, we're going to focus on mainly the hydrophobic and the super hydrophobic parts. When we measure contact angle, we take the angle at which the solid, liquid, and the vapor in the air meet. And when we measure that angle, it's the surface and then the vapor angle. Surface and the liquid angle. So at that angle, we call that the contact angle, and that can be used to determine hydrophobicity, hydrophilicity, superhydrophobicity, or superhydrophilicity, as you can see above. We don't need to really worry about superhydrophilic or hydrophilic right now. We just want to focus on the superhydrophobic and hydrophobic because that's what we're mainly going to be covering in this presentation. Now, overall applications of hydrophobicity. They're essential for water equipment if you go swimming, on flippers, stuff like that. And scientists are always, even people, we're always looking for cheap, efficient sources for super hydrophobic coatings for everyday items like our phones, phone cases, all the stuff like that. Current research shows that, so the eco-friendly molecule we're using is called a it's in the broad category of something called a phospholipid. So current research shows that phospholipids right now are only being used to make superhydrophobic surfaces superhydrophilic. What we want to do is turn that around. And current coatings can be toxic, like naphtha, and you'll hear from Grace when she introduces Never Wet, a product we use a lot here for many fun activities. Many of the chemicals in Never Wet can be very toxic for people. And other superhydrophobic coatings can be very expensive to make. For example, carbon nanotubes, very expensive to synthesize. So, our experiment involved a two-step process. Now, you'll see in these beautifully made images by me and Grace. Over here, we use copper metal, and we have tiles of it. So, we first start off by sanding the copper metal to get micro-rough surfaces, as you see on the screen. So you can see those are the... Okay, thanks, Mike, for blocking my path. Those are the small micro-rough surfaces. And then we soak it. Step one is soaking it in a silver nitrate solution to deposit silver metal nanoparticles on the surface so that we increase surface area, and that way we get a nano-rough surface. After that, step two, we have our phospholipid solution. We soak it in there so that we can attach the polar part or the water-liking part of the phospholipid to the metal, and then the water-fearing part or the water repellent, it's called the lipid part, it faces away, so it repels any water. And so when we put the silver particles on there, more phospholipids can attach than previously just with a micro-rough surface.
So like Akash mentioned, Never Wet is one of the current products on the market, and it's pretty toxic with butane and propanol inside. And Never Wet can also give eye and skin irritation along with some possible brain and nervous system damage. So this leads us to our research question of, is there a more cost-efficient and environmentally friendly way to alter surface wetting properties? And the impact of our research is that research seeks to find an eco-friendly solution to alter surface wetting properties. And this can be applied to ships, pipes, etc. It can make the pipes and stuff more efficient and more resistant to water. And it can also replace, like, as I said before, Never Wet, and also TBT, which is used to coat ships, but then it's actually kind of toxic to sea life. And our goals for this experiment is pretty much to use a naturally found and more cost-efficient molecule to make a surface hydrophobic.
Okay, so like Akash mentioned before, the molecule that we chose to use is called a phospholipid, and it's basically a type of fat molecule, and it makes up the plasma membrane found in all cells. And the phospholipid made up of a polar hydrophilic head, which means that it attracts water, and a nonpolar hydrophobic tail, so it repels water. And the specific type of phospholipid that we used is called lecithin, and we got it from a supplement from soy lecithin. And the phosphate group right here in the head is the part that reacts with the metal ions. And lecithin is a very cheap material to get. We got 1,200 milligrams of it for $6. In comparison to the DCT that we used, we got a 96% purity, only 50 milligrams for $60. Milliliters. So this is we chose phospholipids because they have very similar structure to the DCT, meaning that this side is the polar side and one side is nonpolar, so then the polar side can attach to the metal surface and then the nonpolar side can stick out and repel the water. So we believe that the lecithin can turn the surface hydrophobic, and here's a zoomed in image of what it would look like. So here you have the micro rough structures from sanding the copper, and then the nano rough structures from the silver, and then we attached the phospholipids to the surface. And just to remind you again what our procedure was, first we took a copper tile and we sanded it to create microstructures and to also remove the oxidized layer on the top. And then we soaked it in silver nitrate for 90 seconds to then attach silver nanoparticles to the surface and create more surface area so that we could attach our polar and nonpolar molecules. And then we dropped water onto it and used an optical tenshiometer to measure the contact angle.
And so in order to get these lipids onto the nanorough surfaces, we had to soak it in some sort of solution. And when these phospholipids are suspended in the solution, they tend to self-assemble into these things called micelles and bilayers, with the polar hydrophilic head poking out, which is not what we want for our monolayer, in which the lipid tail would be poking out. And so we dissolved it into hexane, water, and ethanol to see which one would prevent the formation of these micelles or bilayers. And we found that it dissolved the best into ethanol, and water it did not dissolve too well in and did not coat it very well. And hexane, it dissolved almost entirely.
This is the result of our first trial. And you probably can't see a big difference between the four on the left, but you can see that on the right, which is a control, sanded plus silver, it's flatter than the rest. So this is a closer up look of the contact angle of our third trial using an optical tensiometer. So the optical tensiometer gives us a more exact estimation of our contact angle. Copper plus silver was 82.1, that was our control. Copper plus silver plus DCT was 130.7, and copper plus silver plus ethanol in lecithin was 128.8. As you can see, the last two were pretty similar. This is a graph of our contact angle of different coatings on copper. This is our first trial using the optical tensiometer. So silver nitrate, which was our control, was 118.3. Silver nitrate in DCT was 120.5. Water in lecithin was 111.1, and ethanol in lecithin was 125.1. Hexane plus lecithin was 118.6. So from here, we can see that ethanol in lecithin could potentially replace other coatings as a more cost-efficient and eco-friendly alternative. However, more testing is needed to ensure the accuracy of our data. And also, we think that water in lecithin did not result in a relatively high contact angle because water was not soluble in lecithin. Lecithin was not soluble in water as it was in ethanol and hexane. So this is another graph of the contact angles of different coatings on copper, but we did 4 more trials to improve the accuracy of our data. Silver nitrate averaged about 93.9, silver nitrate in DCT averaged about 128.9, and silver nitrate plus lecithin plus ethanol averaged about 122.3. Even though our silver nitrate and lecithin ethanol came out to be lower than silver nitrate plus DCT, we still proved it to be effective because it was higher than our control, which was just silver nitrate. We think that to improve our eco-friendly coating, we could potentially increase the amount of lecithin that was dissolved in the ethanol, since we did use a relatively very small amount.
So the real big takeaway from our experiment is just proving that phospholipids and a naturally found and occurring substance can in fact replace a synthesized alcohol in making a surface hydrophobic. Phospholipids have the potential to make much more cheaper and much more readily abundant hydrophobic coatings, and as shown by our experiments, it is not at too much a cost of performance. And so with this knowledge, some future directions we could take is further optimizing our cost efficiency by replacing the type of metal we use for our nanoparticles. We use silver because that is what we were supplied in the lab and it acted as a control for us. But if we could replace it with something that's maybe not a precious metal, it could potentially decrease the cost even further. We could also do some more different types of testing with degradation in saltwater or freshwater for further application on boats. And to tie into that, more drag efficiency and testing water adhesion rates, again, thinking more towards boats, and also the toxicity and biological effects towards humans or other wildlife or the environment in general. And hopefully, if we had more time, we could have done this on our own, but perhaps these can be explored in the future. Thank you for listening. I think we will be opening the floor to questions now.
Yeah, go ahead. Sure. Okay. So the question was, when we were doing our literature searches, did we find any similar type of research that we're doing right now, where they use phospholipids to coat similar surfaces that we're doing? Correct? Is that the question? Okay. So when we did our research, I don't know about you guys, but when I did my research, I found the article about where they were using phospholipids to make super hydrophobic surfaces hydrophilic. So that's what we put on our presentations. That's the only thing I was able to find on the current applications. Otherwise, I couldn't find anything else about using phospholipids to make surfaces super hydrophobic. If you guys have anything to add. Okay. Yeah. Sure. So the question was, do you want to go?
Well, I think that the question was whether we think that like in the future we might want to look into temperature degradation, and I think definitely. I came up a lot in my research about how to prevent the formation of micelles and bilayers. That the big factors that went into it were temperature and pH, and I think that in the future when we're looking at actually applying this practically, we should definitely look at those two factors and.
This was mainly just seeing if phospholipids really could work as a replacement, because going into this we were unsure if like the phosphate head would bind to the nanoparticles or if like it would just completely form bilayers or micelles and it wouldn't even work at all. So it was really just more of a proof of concept and not really testing all conditions that it could be under.
So the question was, would it stick to any type of material or do you need like specific material, correct? Okay. So the whole point of having the polar, non-polar aspect of it is so that the polar phosphate head can stick to the metal. Because they're both polar in their own ways, right? So the polar phosphate head sticks to the metal. This application wouldn't really work for plastics. So you'd have to develop other products to work on plastics. For example, Never Wet, it works on things like paper, plastic, everything like that. But this is what we're trying to replace on metals right now. Yeah. So your question was, so since cooking sprays use soy lecithin, is there any way we could compare how that process works to how we use nanoparticles to do that?
So are you wondering like how nanoscience was like applied into this? So we actually tried in another experiment, just soaking it in the hydrophobic coatings like DCT or lecithin, with just sanding the copper, not putting the nano rough silver particles in it. And actually, we found really no noticeable difference in the contact angle between just regularly sanded copper and the sanded copper in like DCT, soaked in DCT or lecithin. So it really highlighted how important the silver nanoparticle structures on the micro rough surfaces were in order to make a surface hydrophobic.
Go ahead.
They were taken using the optical tensiometer, and then the droplet was using a micropipette, so like the droplet would be the same amount for all features.
Any other questions? Yeah.
So one of the problems with a lot of these types of sprays like Everwet is that eventually the coating comes out, right? So how would you think about testing your method of putting on this phospholipid to see if it can last at least as long as Everwet or maybe longer or somewhere else? How would you do that?
So how would we test for that? Okay.
We kind of would just like try it on boats first, see how long it lasts compared to the other competitors in the industry.
I think also if we try like exposing it to each of like the different factors, like I was talking about temperature and pH, and we could also look at salinity and other different particles and like exposing them individually and seeing which ones have the most effect on degradation and trying to see how we can reduce that effect.
Which kind of hurts you. We would probably do some type of similar testing we do here, but just we put it under like some type of consistent flow of water.
Yes.
Time and then test after each,
Right. And just to add on to that, we wouldn't necessarily have to be testing on a boat itself. We could just take metal samples that the boats are made out, the hulls of boats are made out of, and just start with that. Yeah, sure. Mhm. So your question was, how would we figure out the concentration of phospholipid on the surface? Well, I'd say we soaked the two metal samples in the same concentration of DCT solution and the same concentration of phospholipid solution. I think they were both. What slide was that? Yeah, it was 0.001 molar. And so when we were given DCT to work with, that was originally at 0.001 molar. And then so we just adapted our phospholipid to be 0.001 molar. And so I'd say it'd be like pretty close to that concentration because the particle size is it's a little different, but it shouldn't play that big of a role in like how much surface area it covers. Plus we have the silver nanoparticles, so we're going to get even more on top of that. Sure, go ahead. Yeah. We may or may not be international criminals. Currency may have been defaced. No, but in all seriousness, we did conduct some studies to see if as one of these guys had said, to see if silver nanoparticles played a big role. So we had to end up sanding pennies for hours. That was not a very fun process, I'll tell you that. And we tested them by soaking, but just leaving them as is, sanded zinc, and then soaking the sanded zinc in DCT and phospholipid solutions, and it made no real difference. So, no, those were just like proof of concept. Then again, so we just use zinc and we use zinc, stainless steel, copper, and aluminum. Any other questions? Yeah. Time frame as in like how long they were soaked in solution?
Like as soon as the droplet was dropped onto it, we took like a picture.
So how an optical tensiometer works, just to add on to what Raphael was saying, is you have the surface and then you put it in front of the camera and then there's a little needle that drops a drop of water while you see the camera. So you can take a snapshot right there. Any other? Yes, Andy.
You guys touch the never wet all the time yesterday when we were doing the and that is your dead. Not that toxic. We're not exposing them to toxic.
Yeah.
Okay, it's not like super toxic, but organic molecules are definitely a better alternative.
Yeah, and like the fumes of never wet can also be.
We never mentioned those. Any other mind-boggling questions? All right, thanks for listening.